Today I've got this interesting exponential diophantine equation that I found in the Math magazine. We're going to solve it. So in particular, we're going to find all non-negative integers a, b, c, and d satisfying this equation 3 to the a times 4 to the b plus 5 to the c equals 7 to the d. And this is going to involve a lot of casework and reduction modulo n for special values of n. So let's start with our first case, which is the case when d is odd. And of course, if d is odd, then we can write d as 2 times n plus 1, where n is bigger than or equal to 0. Given that, we know that d itself is bigger than or equal to 0. But now, let's just plug this version of d into our equation. So that means we have 3 to the a times 4 to the b plus 5 to the c equals 7 to the 2n plus 1. But I'm going to write that as follows. I'm going to write that as 7 times 49 to the n. Given that 7 squared is 49, I think that's a pretty obvious way to do this. But now what I'll do is reduce this thing modulo 4. And why is 4 a good choice? Well, we've got a 4 right here. And we know that 5 is congruent to 1 mod 4. In other words, its remainder is 1 when divided by 4. And then this 7 right here is 3 mod 4, and then 49 is also 1 mod 4. 49 is 1 more than 48. So let's reduce this thing mod 4 and see what happens. So let's just say that this arrow is a reduction mod 4. So that means I'll have 3 to the a times 4 to the b plus 1 is congruent to 7, which is 3 mod 4. Okay, so we've got something like that at the moment. You might say, well, why do I have this 4 to the b? Well, observe that b could be equal to 0, in which case 4 to the b is simply equal to 1. Notice if b is bigger than 1, then this part is definitely 0 mod 4. Okay, so anyway, let's see what we have now. So we can subtract this 1 over, and we'll have 3 to the a times 4 to the b is congruent to 2 modulo 4. But now observe that this is not 0 mod 4. But since this is not 0 mod 4, then that means that this b must be equal to 0. Because otherwise, the left-hand side would be 0 mod 4. But that means we'll have 3 to the a is congruent to 2 mod 4. But that means that 3 to the a is even. Because anything congruent to 2 mod 4 is pretty clearly even. Those are numbers like 2, 6, 10, 14, so on and so forth. But 3 to the a is clearly not even, so that means we've reached a contradiction, contradicting kind of our assumption that we had a solution up here. Okay, so now let's move on to our next case. So case 2. And that'll be the case when d is even and we have c is odd. So it would be nice if we could just have two cases, d is odd and d is even, but you'll see that we will not be able to just have two cases. Okay, well that tells us that c is equal to 2 times m plus 1, and d is equal to 2 times n, with m and n both bigger than or equal to 0. Okay, cool. And now let's plug in those versions of c and d into our equation. So that's going to give us 3 to the a times 4 to the b plus, well, 5 to the c, but I think we can pretty quickly write that as 5 times 25 to the m, using a similar simplification like we did right here with the 7 to the 2n plus 1. And then let's see, we'll have 7 to the d, but that's going to be equal to 49 to the n power. So something like that. And now what we'll do is reduce this mod 3. And you might say, well, why mod 3? Well, notice that 49 is 1 more than 48, and 48 is, well, most definitely a multiple of 3. So 49 is congruent to 1 mod 3. That means 49 to the n is congruent to 1 mod 3. And then 3 is congruent to 0 mod 3, of course, unless a is equal to 0. Okay, so anyway, what we'll do here is reduce this thing mod 3. So let's just say now this orange arrow means reduction mod 3. So that's going to give us 3 to the a times 4 to the b, but 4 is congruent to 1 mod 3. And then plus just 5, because 25 is also 1 mod 3. So, but 5 is 2 mod 3, because it's 2 more than a multiple of 3. So this is 3a plus 2 is congruent to 1 modulo 3. But let's observe that we can subtract 2 from both sides, and we'll have 3a is congruent to negative 1 mod 3, but negative 1 is the same thing as 2 mod 3. But notice that that is also impossible. So if a is equal to 0, then 3 to the a is congruent to 1 mod 3. And if a is bigger than 0, it's kind of obviously 0 mod 3. So never is it 2 mod 3. All right, so now let's move into our next case. So case 3. And this is going to be the case when c and d are both even. But in fact, we can't just have them both being even alone. They'll have to both be even and be different types of being even. But what do I mean by that? Well, I mean something having to do with its divisibility by 4. So our first case of them both being even will be c and d are both congruent to 0 modulo 4. But that tells us that c could be written as 4 times m, and that means that d can be written as 4 times n. Okay, but now plugging that into our original equation and moving some things around, in particular moving this 5 to the c over to the other side of the equation, that gives us 3 to the a times 4 to the b is equal to 7 to the power 4n minus 5 to the power 4m. But of course, we can factor that a couple of times using difference of squares, but we'll really only need to factor it once using difference of squares, and that will be like this. So I'm going to write this as 49 to the n minus 25 to the m, and then 49 to the n plus 25 to the m. Just keeping in mind here that I'm really thinking about this 49 as 7 to the 2n, and then this 25 to the m as 5 to the 2m. So that's just simply a difference of squares factorization where I've, squared 7 and 5 to make it a little bit simpler. Now what I'll do is I'll take this second term, this 49 to the n plus 25 to the m, and investigate that a little bit. So let's observe that 49 to the n plus 25 to the m is what? Well, I think we can pretty clearly see that this is congruent to 2 modulo 12. So how do we see that it's congruent to 2 mod 12? Well, notice that 49 is 1 more than a multiple of 12. It's 1 more than 48. 25 is 1 more than 24, which is a multiple of 12. So this is 1, this is 1. 1 plus 1 is 2 mod 12. But that means that 49 to the n plus 25 to the m is not divisible by 12. Well, that's pretty clear. It's 2 mod 12. It has a remainder of 2 when dividing by 12. But if it's not divisible by 12, that means it's not divisible by 3 and it's not divisible by 4. So let's see, 49 to the n plus 25 to the m is not divisible by 3 or 4. But if it's not divisible by 3 and it's not divisible by 4, yet it is a divisor of 3 to the a times 4 to the b, that means that it must be equal to 2 or 1. So let's see, we've got 49 to the n plus 25 to the m is equal to 2 or 1, but let's observe that it cannot be equal to 1 because each of these is bigger than or equal to 1. Well, since each is bigger than or equal to 1 and each is a positive integer, that means each of these is equal to 1. But if each of these is equal to 1, that means that m and n are both 0. So we have m equals n equals 0. But now let's swing that back up into this portion of our equation and observe that that tells us that 3 to the a times 4 to the b is equal to 0, because we'll have 7 to the 0 minus 5 to the 0. But of course, that is impossible. You can't have a product of things like that being equal to 0. So that gives us another contradiction. So far we have no solutions, because any assumption with solutions built off of these types has proved to be impossible. Okay, so now let's move on to our next case. All right, so here's a summary of our first 3 cases, all of which led to no solution. So now let's move on to our next case, when C and D are congruent to 2 mod 4. So let's observe that that means that C can be written as 4 times m plus 2, and D can be written as 4 times n plus 2. And now let's swing that into the version of this equation right here that we used in case 3. So that's going to give us 3 to the a times 4 to the b is equal to, I'm going to write this as 7 to the 4n plus 2 minus 5 to the 4m plus 2, which kind of pretty quickly factors as 7 to the 2n plus 1 minus 5 to the 2m plus 1 times 7 to the 2n plus 1 plus 5 to the 2m plus 1. So to something like that. Now let's look at this first term in this case. So let's bring this down and observe that we can write it as 7 times 49 to the n minus 5 times 25 to the m. And now if we reduce that thing mod 12 again, observe that the 49 is 1, the 25 is 1, and we're left with 7 minus 5. In other words, we're left with 2 modulo 12. But now we're in the same sort of situation as we were before. So that means that this term right here that's underlined in blue is not divisible by 12. That means it's not divisible by 3 and it's not divisible by 4. But that means that it must be equal to either 2 or 1, because those are the only divisors over here that are not also divisors of 3 and 4. But now we can do the same kind of argument that we did before. So this term right here is congruent to 2 mod 12. That means it's not divisible by 3 or 4. That means that it must be equal to 2. But if it's equal to 2, that means that I can write 7 to the 2n plus 1 as 2 plus 5 times, or 5 to the power 2m plus 1. Again, that's because this thing must be equal to 2 by our previous argument. Okay, but where can we go from there? Well, now we can plug this version of 7 to the 2n plus 1 into the right-hand side over here and produce this equation. So we have 3 to the a times 4 to the b is equal to 2. Recall that this term had to be 2. And then after that, it's 2 plus, well, 5 to the 2m plus 1 plus 5 to the 2m plus 1. But after rewriting a little bit, that's the same thing as 10 times 25 to the m. But now what I want to do is divide both sides by 4. I guess I'm assuming here that b is not 0, but I think it's pretty clear that b is not 0, because that would make the left-hand side odd, but the right-hand side even. Okay, so dividing by 4, we have 3 times 4 to the b minus 1 is equal to 1 plus 5 times 25 to the m power. So we're left with something like that. Now what I want to do is reduce this thing modulo 8. So if we reduce this thing mod 8, let's observe that 25 is 1 mod 8. It's 1 more than 24. So we have 1 plus 5, which is 6 mod 8. So we have all of this is 6 mod 8. But now let's observe that since 4 to any positive number will be 0 mod 8. That means 4 must be raised to the 0 power here. In other words, b must be 1. But that means that we can simply write this as 3 to the a is congruent to 6 modulo 8, like that. And now we can use the fact that 3 is invertible mod 8 because it's relatively prime to 8. And then we can divide by the modular inverse of 3 mod 8. So if we do that, we'll get 3 to the a minus 1 is congruent to 2 mod 8. I guess here we're assuming that a is bigger than 0, but if it's equal to 0, well then clearly this is not satisfied already because we have 1 is congruent to 6 mod 8. Okay, so we're left with something like this. But now let's observe we're in a problem situation here. I guess we were already in a problem situation because the left-hand side here is odd, whereas the right-hand side was even. So that gives us a contradiction for this setting as well, meaning that we still do not have a solution. Okay, so let's move on to our next case. So now let's look at the next, well, what's really a subcase of when both C and D are even, when C is 0 mod 4 and D is 2 mod 4. But let's observe that that means we can write C as 4 times m and D as 4 times n plus 2. Okay, so now let's swing that into our original equation. Well, the version of it with 7 to the d minus 5 to the c. And here we'll have 3 to the a times 4 to the b will be equal to 7 to the power 4n plus 2 minus 5 to the power, let's see, 4m. And now we can do a difference of squares factorization just as before. And that's going to factor, after rewriting it a little bit, as 7 times 49 to the n minus 25 to the m, and then 7 times 49 to the n plus 25 to the m. Okay, so now we're left with something like that. And now what I want to do is focus on this first term a little bit, the one with the minus sign. And let's see if we can explore that. So let's observe that we have 7 times 49 to the n minus 25 to the m will reduce to 2 mod 4. So how do we see that it's 2 mod 4? Well, let's see. 49 to the n is 1 mod 4 because 49 is 1 mod 4, and 25 is also 1 mod 4. 7 is 3 mod 4, so we've got 3 minus 1 or 2 mod 4. But it is congruent to 0 modulo 3. That's because we have 7, which is 1 mod 3, and then this is also 1 mod 3, and then the 25 is also 1 mod 3, so 1 minus 1 is 1 mod 3. Now that doesn't help us quite as much as it did before, but now we have 7 times 49 to the n minus 25 to the m can be written as 2 times 3 to the k for some power k here. How do we know that? Well, it's 2 mod 4, which means it's even, but it's not divisible by 4. And so that means it's just 2 times an odd number. But the only odd number that can be a factor is 3, given the fact that this left-hand side only has prime factors of 2 and 3. Okay, but now we can like invert this equation, if you will, to write 7 times 49 to the n as 2 times 3 to the k plus 25 to the m. And now we're going to swing that back into this equation right here, and we'll be left with 3 to the a times 4 to the b is equal to 2 times 3 to the k times, let's see, 2 times 3 to the k plus 2 times 25 to the m. And that's just from replacing the 7 times 49 to the n with what we have over there. Now we can divide both sides by 4. We'll have 3 times 4 to the b minus 1. I guess here you need to argue that b is bigger than or equal to 1, but the right-hand side is kind of obviously a multiple of 4. And then that's going to give us 3 to the k, and then we'll have 3 to the k plus 25 to the m. We divided 2 from both of those parts. Okay, cool. But now let's observe that this thing right here, this 3 to the k plus 25 to the m, is either congruent to 1 or 2 modulo 3. So notice if k is bigger than 0, it's going to be congruent to 1 mod 3 because it's 25. And if k is 0, it's 1 plus 1 or 2 mod 3. The important thing is it's not a multiple of 3. But since it's not a multiple of 3, that tells us that a and k are the same. But if a and k are the same, that means we can divide them from both sides of the equation, and we have 4 to the b minus 1 is equal to 3 to the k plus 25 to the m. And now what I want to do is reduce that thing modulo 8. But if we reduce that mod 8, we'll see that we get 4 mod 8 when k is odd. Because if k is odd, this is congruent to 3 mod 8. And then if k is even, we get 2 mod 8. Like I said, that's when k is even. But notice we can't have it congruent to 2 mod 8 because this over here is either, well, 1, 4, or 0 mod 8. 1 if b is equal to 1, 4 if b is equal to 2, and 0 if b is bigger. So anyway, this is not possible right here, meaning that the only thing left is 4 mod 8. In other words, b is equal to 2. Okay, so let's observe that we know that b is equal to 2. Let's collect that over here, and then, well, maybe plug that into an earlier part of the equation and see what we get. So plugging in b equals to 2 into one of the last equations that was on the last board, we had the following. We had 4 was equal to 3 to the k plus 25 to the m. But observe that the only way for 4 to be equal to something like that is for k to be equal to 1 and m to be equal to 0. But let's recall that k was the same thing as a. I could have just written an a here. So that means up here we have a equal to 1. And then let's observe over here that c is 4m. So 4 times 0 is 0. So that means we have c equal to 0. And now we can loop that back into our original equation, and we'll very, very quickly have what d is. Actually, we don't need to futz around with this at all. We can just plug it in over here, and we'll have 7 to the d is equal to, let's see, we'll have 3 times 16, which is 48, plus 5 to the 0, or 1. We have this is 49, which means we get d equal to 2. Okay, so now let's collect that over here. We've got a solution. A equals 1, B equals 2, C equals 0, and D equals 2. Okay, cool. But what we have left is a single case. So let's write that right here. Case, let's see, it will be 6. And that'll be the case when what happens? We'll have C congruent to 2 mod 4. And we'll have d congruent to 0 mod 4. That's the only thing that's left. But actually, let's leave that as a homework exercise. Maybe post in the comments what trick you used. Did you use something new, or did you develop something from what we did in these previous cases? And that's a good place to stop.